Welcome to Lecture 3-2, Establishing Validity in Research Designs. This is the first part of lecture on this topic. I've divided it into two parts. In this lecture, we will talk about statistical conclusion validity and internal validity. Construct validity and external validity will be discussed in Lecture 3-3. So those are the four major types of validity in quantitative research. Statistical conclusion validity refers to the ability to make an accurate assessment about whether the independent and dependent variables are related and about the strength of that relationship. So again, the two key questions here are the variables related and how strong is the relationship? Note that this question involves the measured variables, not the program constructs themselves. Thus, it's very narrow in scope. Ultimately, we do not really care about the relationship between two narrowly defined measured variables, but about the relationship between the program and the program outcomes. We must use the measured variables to test that relationship, to evaluate that relationship. Typically, this is done through something that you're going to be learning about in another class, the null hypothesis significance testing. We'll be studying that in Political Science 6003, the Research Techniques class, which will come later in your MPA curriculum. The null hypothesis significance test is used to determine whether two variables are related in the population from which the study data were selected. This procedure will tell you whether a relationship is statistically significant or not. We can also use measures of correlation to gauge the strength of the relationship. For now, just remember that a relationship is said to be statistically significant when we do not believe that it is nothing but a chance occurrence. The logic of hypothesis testing is a bit difficult to grasp the first time you hear it. Yes, I did use a double negative there. We do not believe that it is nothing but a chance occurrence. And a relationship is not statistically significant when the null hypothesis testing procedure says that any observed relationship between two variables is probably nothing more than what we refer to as sampling error. To determine how strong a relationship is, researchers use what are called effect size indicators. Again, this will also be discussed in the 6003 Research Techniques course. There are many different effect size indicators that you'll be studying in that course, but they all tell you how strong a relationship is, and most of them tell you what direction the relationship is as well. Again, for now, remember that the answer to the first key question, are the variables related, is answered using null hypothesis significance testing, and the answer to the second key question is answered using an effect size indicator. Internal validity is defined as the approximate validity with which we infer that a relationship between two variables is causal. So it's usually considered unfair to use the word validity, or use a word in defining itself, and here I've used the word validity, quoting from Cook and Campbell, to define validity. What does it mean if something is valid in your own words? Pause and think about that for a moment. Many of you probably came up with something along the lines of, it means it's true, it means it's real. And I think those are fairly decent definitions or fairly decent approximations of the word validity. So a good synonym for the term internal validity is causal validity. As I said a moment ago, quoting from Cook and Campbell, we can infer that a relationship between two variables is causal. So causal validity. If you can show that you have high internal validity, in other words, high causal validity, then you can conclude that you have strong evidence of causality. However, if you have low internal validity, you must conclude that you have little or no evidence of causality. So what do we mean by causality? Traditionally, scholars who study this, scholars ranging from political scientists and social scientists in general, to even physical scientists and certainly philosophers of science, discuss three initial conditions for establishing causality or causation. So these are the classic three conditions. First off, we have temporal asymmetry, which simply means that the cause precedes the effect. The cause precedes the effect. So far as I know, no one has invented a time machine to allow us to go back and produce an effect before a cause or after, or to produce a cause after an effect. We normally think of time as flowing in only one direction. I know that it's possible to at least conceive of alternatives to that, but so far as we're concerned for this class, the cause has to precede the effect, or to use the language of program evaluation, people should receive the program treatment, whatever it is the program is doing, before there is a change in the dependent variable, before the outcomes occur. The second condition for causation is that we must establish there is covariation between the independent and the dependent variable. We have to show that the independent variable and the dependent variable vary together. As the independent variable changes, changes are noticed. I don't say the word produced, but noticed in the dependent variable. I use that word noticed because what we're trying to prove is that we can use the word caused or produced. So ultimately, when we establish all three of these things, we will make a statement to the effect that the covariation between the program and the outcomes is causal, that the program causes, the program produces the changes in the outcomes. Or to go back to the level of the variables, that the independent variable produces or causes the changes in the dependent variable. The third condition for establishing causation, and one of the most difficult, the one we're going to spend a lot of time talking about now, is that there are no plausible rival hypotheses. What that means is that we can eliminate any third or fourth or fifth variables out there, any third or fourth or fifth possible causes that are actually producing the changes in the outcomes, that are actually producing the changes in the dependent variable, and not the program itself. So this is what it means. This third one is really what establishing internal validity is all about. The threats to internal validity, for the most part, that we'll be discussing are not about establishing temporal asymmetry or about covariation. Temporal asymmetry, by and large, is established based on our knowledge of the world, what comes first, what comes second. There's a bit of measurement involved in that. Covariation between the independent and dependent variables is part of what goes on with statistical conclusion validity. So most of what we're dealing with now in terms of internal validity is related to this plausible rival hypotheses topic. Now again, just to review, I've been using a lot of words here interchangeably. You need to study this particular slide, this particular diagram, and make sure you understand the relationship between these various pairs of words. Cause and effect, the x and y variable, the independent variable and the dependent variable, the program component, and the observed outcomes. Those are four different ways of saying the same thing. Typically in evaluation research, we're talking about a program or a program component, which ultimately we hope to prove causes the observed outcomes. For shorthand, we often refer to the independent variable and the dependent variable. The independent variable will be the same thing as the program or the program component. The dependent variable, the observed outcomes. So basically the relationship between the independent variable and the program component is this relationship between a variable, an observable, measurable thing, and the idea behind it, the program. The same goes for the dependent variable and the observed outcomes. We also, typically, as I have been doing, refer to these things as causes and effects. And for shorthand, many researchers and certainly many instructors have adopted the x and y names for the independent variable and the dependent variable. It's simply much easier, much quicker to say x and y. X causes y. And in fact, we also have adopted another shorthand, not shown on here, when we are looking at these possible third variables out there that might be causing the differences in the y variable. Instead of our program, we often refer to them as z variables. So x, y, and z. Finally, the last two pairs of things on the slide: causal description versus causal explanation. These are discussed in the book, and I wanted to take a moment to review them for you. Causal description typically involves simply describing the consequences of manipulating an independent variable. In general, causal description involves showing that changes in the variable x, the independent variable, cause changes in the variable y, the dependent variable. Oftentimes, this is sufficient. If we can show that a manipulation produces a change, we're pretty happy. However, typically, maybe, or certainly often, we want to go beyond mere causal description and delve into the realm of causal explanation. Causal explanation involves more than simply describing we change x and y changes. It involves explaining the mechanisms through which and the conditions under which a causal relationship holds. You might think of this as teasing out the linking constructs between the program and the outcomes. It's telling a story about why when x, I shouldn't use y that way. It's telling a story about how and why when our x variable changes, our y variable changes. It's telling a story about how and why our program ultimately produces the outcomes. This involves the inclusion in your research study of what are referred to as mediating variables, intervening variables, moderating variables, which are basically different names for the variables that come between x and y. In other words, names we give to the way we measure linking constructs. Finally, we have extraneous variables and confounding variables. Extraneous variables are variables that we've managed to eliminate. Typically, extraneous variables then refers to the idea of any variable that may compete with the independent variable in explaining the outcome of a study. These are our z variables. Okay, so an extraneous variable may compete, may be an alternate explanation. A confounding variable, sometimes referred to as a third variable, is basically an extraneous variable that we have confirmed does compete. Okay, a confounding variable is an extraneous variable that we've managed to establish does cause us a problem. Does cause a problem because we know that it does have a relationship with the independent and dependent variables. A confounding variable is a variable that systematically varies or influences with the independent variable and also influences the dependent variable. When you design a research study in which you want to make a statement about cause and effect, you must think about what extraneous variables are probably confounding variables and do something about it. Let me give you a brief example to illustrate this. Everybody has seen the Pepsi Challenge. In the Pepsi Challenge, people are brought to a little table. There are cups of soda sitting on the table, and they're asked to taste the beverage in the two different cups and draw a conclusion about them, which one they like better. So anything that varies with the presentation of the Coke or the Pepsi is an extraneous variable that may confound the relationship. In other words, it's an extraneous variable that may also be a confounding variable. For example, perhaps people are more likely to pick Pepsi over Coke if different letters are placed on the Pepsi and Coke cups. Oftentimes there's a letter A and a letter B on the cups. If people somehow subconsciously prefer the letter A over the letter B, then that's a confounding variable. Or if the cups are red and blue. If people prefer red over blue, that's a confounding variable. In short, we must always worry about extraneous variables when we're interested in conducting research that will allow us to make a conclusion about cause and effect. So, throughout the text and throughout this discussion, this lecture, I will be using, and you have read, this phrase, threats to internal validity. Basically what we have here is a list of the possible things, the possible ways in which third variables can call into question our third necessary condition for causality. These are typical scenarios in which a plausible rival hypothesis occurs. Most of this is drawn from the work of Campbell and Stanley, dating back to 1963, although there have been a number of sort of updates to this. So these threats to internal validity, and there's a long list of them. But before discussing the specific threats, I want you to get the basic idea of two, what are typically referred to as weak research designs, into your head. I'll use these designs to illustrate the various threats to internal validity. I suggest you copy them down to consult as you watch the next slides. The first weak design is the one referred to as the one-group pretest post-test design, which is the first of the two shown on the slide. The one-group pretest post-test design. As you'll know from your readings, the O in the design refers to an observation, the X to a treatment, and the next O to another observation. So we have an observation of a group, we treat the group, we observe them again. So we have a pretest and a post-test. For example, you could measure your students' understanding of history at the beginning of a term, then you teach them history for the term, and you measure them again on their understanding of history at the end of the term. Or you would make observations about, let's say you had a drug treatment program. You make observations about how addicts deal with their desire to use drugs. You give them the treatment, and then you measure the techniques, the strategies the addicts use afterwards to deal with their temptation to use drugs. There are many possibilities here in description, but those are just a couple of examples. The second weak design is the post-test only design with non-equivalent groups. Post-test only with non-equivalent groups. In this design, no preliminary measurements are taken. Notice the dashed lines. We have two groups, one of which is given a treatment, the X, one of which is not, and then we take some measurements. Oftentimes we refer to these groups as the treatment group and the control group. Another way to look at it is the folks who receive the treatment, the X, are in the program. The folks who do not are not in the program. Ultimately, what we want to do then is make comparisons of the two sets of observations to see if the people who received the program differ from people who did not. So what we've got here are two basic designs to look at changes. In the one group pretest post-test design, we look at changes in the same people. We look at a group of people, treat them, put them in a program, and observe to see if there have been any changes. In the second group, in the second design, we give one group a treatment, the other group not. One group in the program, the other group not. And then we look to see if they are different. Okay, so if you've got those memorized, just saying a couple more words. So in comparing the two designs just mentioned, make sure you understand we're making two different kinds of comparisons here. Remember this key point. Multi-group designs differ from single-group designs. In some situations they're better, in some situations they're not better. What they are is different. In each of the multi-group research designs that include more than one group of participants, you want the different groups to be the same on all extraneous variables beforehand, and different only in the single fact that the treatment group received the program and the control group did not. Say that again in another way. You want the only systematic difference between the groups to be exposure to the program. The best way to ensure this is through random assignment of subjects to be in the program or not in the program. Random assignment of subjects to receive the treatment or not receive the treatment. But there are many designs that do not use this sort of random assignment. We'll discuss why that is a bit later. But to briefly give you a reminder now, oftentimes it is difficult for ethical reasons or for legal reasons to provide the program to one group of people and not provide it to another. Other times it's simply a logistical problem. So, now I believe we're ready to start talking about these various threats. Remember again, what the threats are scenarios that describe situations that commonly occur or that researchers have noticed to occur in the past that threaten our ability to conclude X causes Y. Threaten our ability to conclude that the program is the reason for the differences observed. These are all discussed in your book. What I'm hoping to do here with the lecture is simply give you a slightly different take, provide you with a different way of taking in the information, maybe give you some examples to help you understand. So the first threat that I'm going to discuss is the history threat. The history threat refers to any event other than the planned treatment, other than the planned program, that occurs between the pretest and the post-test measurement, and that has an influence on the dependent variable, that has an influence on the program outcomes. In short, if both a treatment, the program, and a history event occur between the pretest and the post-test, you will not know whether the observed difference between the pretest and post-test scores is due to the treatment or due to the history event. In short, these two events are confounded. Notice first off that the history event can only occur, or the history threat can only occur, if you have a pretest and post-test type of design. For example, let's say you have a program to combat anti-Muslim prejudice. The program itself lasts several months. During the program, there is a terrorist attack that is attributed to Islamic extremists. The history effect here is a threat for the one-group design, but it is not a threat for the multi-group design. Why would that be the case? Well, in the one-group design, the first of the two designs I asked you to write down or memorize, you take as your measure of the effect of the treatment the difference in the pre-test and post-test scores. In this case, this all or part of the difference could be due to the history effect. You do not know. If there is a change between the pre-test and the post-test, you do not know what caused it. You don't know whether the change in scores is due to the treatment or the history effect. They are confounded. The basic history effect is not a threat to the two-group design, because now you are comparing the treatment group to a comparison group. As long as the history effect occurs for both groups, the difference between the two groups will not be because of the history effect. Of course, that's not true if the history effect only occurs for one group, but that's a very odd occurrence. The second threat to internal validity is called maturation. Maturation is when a physical or mental change occurs over time and it affects the participant's performance on the dependent variable. For example, if you were to measure first grade students' ability to perform arithmetic problems at the beginning of the year, and again at the end of the year, some of their improvement will be due to teaching, the program, and some may be due to their natural maturation. Therefore, in the one-group design, you will not know if the improvement is due to the teacher or if it is due to maturation. Maturation is not a threat in the two-group design because as long as the people in both groups mature at the same rate, the difference between the two groups will not be due to maturation. If you're following this logic about why these first two threats to internal validity are a problem for the one-group design, but not for the two-group design, then you've gotten one of the major points of the chapter. The same logic is going to apply to the next three threats: testing, instrumentation, and regression artifacts. So, testing. Testing refers to a change on the second administration of a test as a result of having previously taken the test. It's a bit confusing when you first hear it, so let's look at an example. Let's say you have a program that you believe will cause students to reduce racial stereotyping. You use the one-group design, and you have your participants take a pretest in which you ask them many questions. You give them the treatment to reduce racial stereotyping, and then you give them a post-test measuring their agreement with certain racial stereotypes, their attitudes towards certain races, whatever. The problem is that perhaps their scores on the post-test are the result of being sensitized to the issue of racial stereotypes because they took the pretest. You made them more aware by asking questions up front. So in other words, actually asking them the questions cause them to think about it, change somehow, and not the program itself. Therefore, in the one-group design, you will not know if the improvement, the change, from the pre-test to the post-test is due to the treatment or due to the testing effect. Testing, again, is not a threat in the two-group design if both groups are pre-tested. Remember, the initial weak design I gave you did not use a pretest, so we would modify that original design I showed you, the second of those two original designs, to take observations of both groups, treat one group and not the other, and then take observations of both groups again. So the two groups differ on exposure to the treatment, but they are the same on exposure to the pre-test. Thus, we can eliminate the pretest as a possible threat. The fourth threat is instrumentation. Instrumentation refers to a change that occurs in the way that dependent variable is measured in the research study. For example, let's say that one person does your pretest assessment of students' racial stereotyping, but you have a different person do your post-test assessment of student stereotyping. If the second person tends to overlook certain types of stereotyping that the first person picks up, you've got an instrumentation effect. Or another example of this would be you ask slightly different questions in the pre-test and the post-test, but the questions themselves aren't equally valid, aren't equally good at measuring racial stereotyping. So in the one-group design, you will not know if the improvement from the pre-test to the post-test is due to the treatment, due to the program, or if it's due to instrumentation. Instrumentation, again, is not a threat in the two-group design because as long as the people in both groups are affected equally by the instrumentation effect, the difference between the two groups will not be due to the instrumentation. So here again, we would be using a pretest for the two groups, treating one group and not the other, and taking a post-test measure of both groups. Regression to the mean. This fifth threat to internal validity is regression to the mean is sometimes referred to as a regression artifact. Regression artifact refers to the tendency of very high pretest scores to become lower later, or for very low pretest scores to become a higher later. Not because of the treatment, not because of the program, but that people who are initially measured at one extreme or the other tend to regress to the mean. This is a very common threat in evaluating programs because oftentimes we choose people to be in programs because they have extreme scores, because they are in poverty, because they are hardcore drug users, because they whatever. We tend to pick people oftentimes to be in many of our programs, public programs, because they have problems. And problems sometimes tend to get better on their own. For example, let's say you select people who have extremely high scores on your racial stereotyping test. Some of these scores are probably artificially high because of transient factors. Therefore, if stereotyping goes down from pre-test to post-test, some or all of the change may be due to a regression artifact. So again, in the one-group design, you won't know if the improvement was due to the treatment. Regression artifacts is not a threat to the two-group design because as long as the people in both groups are affected equally, the difference between the two groups will not be due to the regression to the mean. Now here's where the problem comes in. As I said, oftentimes people are chosen to be in the program based on extreme scores. People who are not in the program don't have those extreme scores. So this is another kind of problem, really. And it's an interaction effect which we will discuss later, but keep it in mind. The sixth threat to internal validity is called differential selection. Differential selection, unlike all the previous threats we've discussed, only applies to multi-group designs. It refers to selecting participants for the various groups in your study that have different characteristics. Remember, we want our groups to be the same on all variables except the treatment variable. The treatment variable is the only variable that we want to be systematically different for the groups. In the chapter, Table 8-1 lists a few of the many characteristics on which people in different groups might differ. Age, anxiety, gender, intelligence, reading ability, lots of different things. And again, as I've indicated a couple of times, oftentimes when we're selecting people to be in a program, we don't do it randomly. We do it for a reason. People who are not in the program are not in there for a reason. So what one needs to do is, first off, have an adequate control group. A control group that is as similar as possible, in fact, perfectly similar, to the treatment group. So one wants to consider, when one is setting up a two-group design, who should be the comparison group. Again, oftentimes it's not possible to do a two-group design for this very reason, that we really cannot find a comparable group, that we really cannot use random assignment to give some people a treatment and other people not. There are ways around that, as discussed in the text, and as we will hear later in the lecture. Unlike the previous 5 threats, as I said, selection is not an internal validity problem for the one-group design, but it is for the two-group design or multi-group design. As an example, assume you select 2 classes for your study on reducing racial stereotyping. You use 2 5th grade classes as your groups. One group will get your treatment, the other will act as a control. The problem is that these 2 groups of students may differ on variables other than your treatment variable. One thing I can think of off the top of my head is that they probably have different teachers. So any differences found at the post-test may be due to these differential selection biases rather than due to the treatment. The 7th threat to internal validity is called experimental mortality or differential attrition. Nobody actually has to die for this mortality to occur, so a lot of people prefer to refer to it as attrition. This simply refers to participants dropping out of your research study. Differential attrition, then, is the differential loss of participants from the 2 comparison groups. Just like the previous threat, differential attrition is a problem for the 2 or multi-group design, but not for the single group design. For example, assume again you're doing a study on racial stereotyping and programs to decrease or eliminate it. Can you see how your result will be compromised if the kind of children that are most likely to have racial stereotypes drop out of one of the groups, but not the other group? Can you see why that would be the case if you are presenting them with material on racial stereotyping? If people who are resistant to changing their racial stereotypes, if people are resistant or uncomfortable with talking about race, they're more likely to drop out of the program, to refuse to be part of the program. So you have these different rates. So the observed difference in the post-test may now be the result of the fact that people in the treatment group who had the strongest stereotypes dropped out. Not that you changed anybody's mind with the program. Additive and interactive effects. It's actually a set of threats. Additive effects and interactive effects refers to the fact that threats to validity can combine to produce a bias in the study which threatens our ability to conclude the independent variable is the cause of the differences between the groups. So this applies to, again, the 2-group or multi-group designs. These threats occur when the different comparison groups are affected differently by one of the earlier threats to internal validity, history, maturation, what have you. For example, just a couple of them. A selection history effect occurs when an event occurring between the pretest and post-test differentially affects the different comparison groups. Selection maturation effects occurs if the groups mature at different rates, and so forth. You should now be able to construct similar examples demonstrating things such as the selection testing effect, the selection instrumentation effect, and the selection regression artifact effect. Remember that the key for the selection effects is that the groups must be affected differently by a given particular threat to internal validity. You've reached the end of Lecture 3-2, the first part of establishing validity in research designs. At your convenience, when you feel you've mastered the concepts here, please proceed to Lecture 3-3, in which I'll be discussing construct validity and external validity.